Evening, everyone. Myself, Prabakaran Chandran. I've been working as a data scientist at Captain Fish. Prior to that, I worked with Mu Sigma on solving different problems across different industry verticals. And now I'm working with them, Captain Fish, in terms of solving marine and inland aquaculture for solving supply chain and procurement problems with the help of remote sensing and artificial intelligence. So, with respect to this Tech for Good Coimbatore edition, I was thinking in terms of like anyhow the problems will be um, around municipal administration or governance. So that's why I've taken this particular topic, remote sensing and artificial intelligence for municipal administration, so that this session will be like one-on-one for those who are interested in landing remote sensing related task, and also how we can actually combine remote sensing along with the artificial intelligence to solve certain problems which are industrial related or also social related. So in this today's session, we'll be discussing the fundamentals of remote sensing and how like what are the different satellites available, and what is the primary source of data, so that we can use it for our use cases, and the spectral indices, the different spectral features that we can use it for remote sensing, and the different problem spaces that are faced by any municipality, and those one or two problem spaces, how we can actually solve it through remote sensing and machine learning. So without delaying, like the remote sensing is nothing but a technique that is used to like gather the information about the earth's surface. The thing is, like we tend to collect data most of the time, like whoever works in usual like data science or artificial intelligence problem statements, we tend to work on data which is already collected through systems, right? Mostly we work on like customer related information, transaction related information, maybe operations like a factory operations, IoT. Through IoT we collect sensor data, right? But all of them are very easy to collect, are very proximal to the users, right? They are part of the systems itself. But the problem is, like when we want to do analysis on scale, when we want to perform analytics on scale, means like over a larger surface area, or it is scattered across multiple locations. So for those kind of use cases, we cannot deploy our people and measure. We cannot spend physical sensors or physical instruments, so that our field executives can go there and check every nook and corners and collect the information and load it to our cloud or some data collection endpoints. Right, this will be a very tedious task, and also people are not interested that much to do this kind of field activities. That's why, like remote sensing is a technique where we are trying to observe certain characteristics of the Earth's surface through the sensors. So here the sensors are nothing but sensors placed in satellites or drones or even aircrafts. So these sensors are nothing but a kind of a camera only. But in usual camera, whatever we use, like mobile phone or Canon cameras, they try to capture RGB, right? Red, green, blue wavelengths. But those wavelengths are limited to certain characteristics. That's why we are going ahead with like an extended wavelengths of electromagnetic phenomenon, right? So I will discuss that wavelengths and all in the next slide, but just to know about what is remote sensing and why it is required. And this is what, like, we cannot reach out every places, and also like for a larger scale of agriculture or ocean marine management, or even asset management for petrochemical companies, or for even for governments to monitor their border lines, right? Like, how are we actually get to know about, like, China has evaded, or China has occupied Indian premises, and then they have built up certain settlements over there. So it's all through like remote sensing, either through satellite information, or Airbus kind of aircrafts, or drones, right? So based on that, we are able to monitor a lot of our assets, or a lot of our area of interest, right? The area of interest could be anything. It can be our agriculture land, or it can be um, like assets, like the petrochemical areas, wells, or even our vessels in the oceans, which is the ships, fishing ships, right? So here, if you see this particular flow, these remote sensing is playing a role of data collection. It's nothing else. It's just doing the like data collection, but the data is not just RGB. It possesses a lot of information in other electromagnetic spectrum, and also it brings us in the various resolution. Like, we can capture images, the satellite images, with 0.5 meter or 15 centimeter resolution. And also there are satellites which are revolving around uh, the earth for every day, which means they're capturing frequencies every day to 5 days or 12 days, right? So where the more and more resolution gives more and more precise data, so that we can get highly accurate insights. So those insights will help us to take certain decisions, right? So so this will be the flow. Like, we get data from different sensors, which is satellite or aircrafts, and then we have the ground stations to process them, because whatever is being captured in the satellite will be like in a scattered, or maybe it might have more noise. So ground stations will have the processing, and once the ground stations process them, that will be stored in Google Cloud or any sort of clouds. So why I put Google Cloud or any other clouds means, like, they are open source, so that anybody can utilize it. And there are a lot of satellite imagery as a service companies which are providing the pay as you go kind of imageries. And we can use Vertex AI or any kind of AI platforms to use those imageries and perform the analysis, so that we can take predictions, like what will be the carbon emission, or what will be the biomass in a certain area, or what will be the yield from a certain agricultural lands. Likewise, we can get predictions. Those predictions will help us to take decisions, like where to deploy our like a procurement, or where to concentrate on, so that we can avoid specific environmental changes. All those things we can do. So satellite imagery is going to be the primary source of data. So there are two different things of broadly, if we speak, like there are two different types of imageries available. One is multispectral imagery. You can see this here, where you can clearly distinguish the bands. Bands are nothing but red, green, blue kind of different channels, right? In multispectral, it is dependent based on the type of satellite imagery that we are using it. Mostly, like, if we use like a satellites like Sentinel. Sentinel is one of the satellite that is being launched by Europe Space Agency. That is giving us 12 different bands, which means 12 different characteristics of a particular element or particular surface can be studied, and all of them are different wavelengths. So it is the criteria or the phenomena is simple. So you are launching, or you are sending a electromagnetic wavelength, which are different in nanometer scale. So based on the characteristics of a particular element in the surface, which you consider buildings, you can consider water or vegetation, based on their reflectance characteristics, the remaining thing will be reflected. So the reflected wavelength will be captured through the satellite. So those informations are being sent out. So if you could see, this is the area where we captured near Marakanam. The same thing you can try it out on Coimbatore or whatever residential area that you are belongs to, right? So this is just an RGB image. But if we could see that in NIR is nothing but near infrared. You can see this here, like we have coastal, blue, green, yellow, red edge, near infrared 2. Likewise, we have different types of bands based on different wavelengths. You can see here, like it starts from 400 nanometer to 1100 nanometer. Afterwards, beyond this, it will be UV. Lesser than this will be microwaves. So it is like different segments of electromagnetic wavelength. And if it is like clearly defined spectral bands, it will be multispectral. For hyperspectral, it will be a continuous spectrum, which means it will capture the entire wavelength limits. For example, here we have limited everything, but in this, like in the hyperspectral, it will be continuous values. We have to perform a lot of dimensionality reduction or like extraction of certain limits of the values that we might do. But with respect to the like usual or very common use cases, multispectral itself is enough. Like with respect to the memory occupy, multispectral will take comparatively lesser memory than the hyperspectral. But here, whenever you talk about satellite imagery, it will not be in KBs or MBs. It will always reach certain GBs or at least more than 500 MBs for a specific use case. Because we are not only concentrating on RGB or spectral bands, we are also concentrating on temporal resolution, which means the satellite rotates the world every day or every 5 day or every week. So we tend to collect more and more data. So in that case, our data points will always be high, and the data storage would also required a lot. But to avoid those kind of like constraints for an individual user or those who are using on their laptops or for prototyping, we have certain infrastructure benefits or even like specific open source tools are available which are meant for handling those issues, right? So this is how the data looks like. And if we compare the wavelength and its reflectance, you can see this like we have different types of entities available in the surface, right? It is man-made structure, soil we have water, rock, minerals are there, and frost or ice, snow, all of them are like related to Arctic, Antarctic things, right? Like snow is there, and then ice or frozen areas. So usually in our places, it will be just man-made soil, water, rock, maybe mineral in some areas, right? Like mining areas. So if you could see this, like the wavelength, which is from 100 nanometer to 500 nanometers, we can see the reflectance pattern. So in a certain areas, like for example, the reflectance of, let me take man-made structures. The reflectance of man-made structures is very high, at most 100% reflectance in the 100 nanometer area. Whereas in the later stage, when you take the near infrared, you compare this also, like for the example, you can consider this as well, like which is less than 1 nanometer to 400 nanometer to 1100 nanometer. That can be converted here also in terms of like micrometers. So the scales will be available in nanometers as well. But if you just consider nanometer wise belongs to certain colors like bands: red, green, blue, near infrared, far infrared, short wave infrared, right? The characteristics are changing. Not all the wavelengths are reflecting in the same quantity. For example, if you take this 0 to 1 micrometer wavelength, the frost is completely absorbing everything, like all the frost or even like the ice. It is not reflecting back anything. But if you take man-made structures here, like the continuous pink color, it is reflecting a less, like around 20 percentage. But if you take minerals, they are reflecting a lot. And the same for rock. And even if you take vegetation, it is comparatively higher. Like you can compare like soil and vegetation. The soil is reflecting more than the vegetation in this particular region, like 0 to 1. But if you go beyond this, like in this one, which is like 1 micrometer or more than that, you can see the shift, which means vegetation reflects certain thing a lot. And this thing like this one, the soil or man-made, is comparatively reflecting. The reflectance is lesser than what vegetation and rock or other things are doing. So this is based on the characteristics of that particular element. For example, if you take vegetation, the vegetation will have chlorophylls in that, right? The plants will have chlorophyll. The plant cells will have chlorophyll, and that chlorophyll is nothing but a pigment, right? That is what the reason of plants are being like plants are being green in color, because of that pigment. That pigment has more like reflectance towards certain wavelength. For example, green will be completely absorbed, or blue will be completely reflected. It is based on the reflections of different colors, right? Whatever we have mentioned here will be based on that. For example, if you take this area, so we have taken a NIR band. So you can see all the vegetations are in red in color, but the water area is black in color, because in NIR, which is near infrared, the vegetation will tend to reflect the NIR completely, whereas the water, it will absorb through it. There won't be any reflection. So likewise, based on different behavior, like let's say even if you take other things like red edge or red color, it will the reflectance will vary with respect to the sources. So this is what the data we are actually collecting it through the satellite imagery, and this particular data will be used for, because if you just see this and this, here we could clearly see the water bodies, right? Because sometimes when we see from the RGB normal lens, normal eye, most of the water bodies would look like green in color only other than ocean, but other water body, because that has chlorophyll content, which is algae grown over there, or some other water plant might be there. So it's same for different lands also. For example, if you just see the land or some other surface in RGB, it might look similar. But if you look in terms of different colors, different bands, like wavelengths, there will be a distinction between um, salt affected land and the normal land, or land which has grass and which doesn't have grass. All those things we'll be able to capture. So that's why the spectral indices or spectral wave bands are important. And this is how the reflectance behavior would look like. So these are the reflectance are captured by the data, sorry, captured by this multispectral imageries, and then we are using it. Right. So we know that, okay, this is how the capture like reflectance are being captured, but what is capturing all of them, or how are we actually capturing it, right? For that only we have um, Sentinel-2. So actually there are a lot of numbers of hundreds of satellite missions are there. Few of them for Earth observation, few of them for communication, few of them for maybe communication for specific use cases like defense sectors, or few of them for specific use cases like oceanography, or few of them is only for mines, which is like underground minerals, right? So one such thing is for Sentinel-2. It is actually used for like various purposes. Sentinel-2 is like a constellation of two different satellites, two satellites which are Sentinel-2A and 2B, and they are actually used for like monitoring a lot of landscapes, for land ecosystem, for inland and coastal water quality monitoring, and they are also using it for like disaster management. So it is actually has use cases across different sectors, majorly aquaculture, agriculture, marine and inland water quality monitoring, and land, right? Usual land surfaces, not for agriculture. Agriculture also we can use, but other than agriculture, we can use it for land use monitoring. And because the reason is like we cannot go beyond this. The reason is Sentinels-2 resolution is 10 meter per pixel. So when we are using it for 10 meter per pixel, we can use it to monitor large in scale entities, not assets like your warehouses, or maybe the assets in petrochemical areas or mining industries, right? For example, wherever we have laid down our pipes or underground pipes, if there are any leakages or if there are any oil spillages, that might be kind of difficult because that area spread might be very less. But for monitoring the large scale things like agriculture, aquaculture, or forest deforestation, or even like flood management, it would be easier, right? And still we even like in industry we still stick to Sentinel-2 because it's open source. We can get it for easily. But when we go for higher resolutions, the cost will be high because this is free, but for higher resolution that will be cost, right? And the data is actually like monitored by like hold by like ESA, and there are a lot of other open source collaborators, those who are bringing this data to the common platforms, which is AWS is there. AWS is providing open data registry where we can download it, or we can also use it through Microsoft Planetary Computers. I will show that. And using this, we are trying to solve certain problems. Even in our industry, we use it for aquaculture monitoring and other use cases. And this is how the Sentinel-2 coverage will look like. So the Sentinel-2 will revisit each and every place in every 2 days. You can see these lines are going like there. This is how it visits. Like here also you can see that the path of Sentinel-2 is in the polar way, so that it can cover larger section quicker way for every 5 days. And this is how the entire world is being tiled, which means it will go or it will fly over a certain area. That area will cover 100 square kilometers, which is 100 square kilometer. So 100 square kilometer will obviously like hold certain area, so that like we'll be able to cover that particular thing. Like for a second, if for a moment it is staying in a particular area, that will cover 100 square meter. But that coverage or that track, right, like the movement will be properly defined. So the world is being divided into equal size of tiles, and each and every tile has so you can see these tiles are being put over this thing, like put over Italy here, like so each and every tile will have certain overlap, so that the data capturing will have like smoothness because of that overlap. And then for every moment it will visit that each and every tile, so that the data will be available in tiled way. It won't cover it is not that one image for entire world. It will be like one image for that particular tile, and that particular tile will be cataloged for a particular time period. Let's say it is like 6:30 11th July 7.1, and it will capture at second level also, right? So after 5 days, it will come to the same area and capture it, right? This will vary based on the time also. It is not like every day, every 5 days same time. It will vary because it has to cover the entire area, and also there is some overlaps, and 2 satellites are there, so those kind of coordinations will be there. And I have just divided the role of, now we can get into remote sensing, analytics, and AI, especially for municipal administration. So I'm just putting this into 2 different buckets. One is analytics, the problems that we can solve it through just an analytics, and problems which we would require AI and other beyond the stuff, right? For example, for any municipalities, like there are problems like with respect to governance, people governance, and also their asset governance. And other than that, they have like other things like urban planning, water quality monitoring, or monitoring their reservoirs, and ensuring the environmental qualities in a particular water bodies, and flood. So flood as in like where flood is affected, and how can we mitigate or to assess the flood damages. For example, you could have seen, like whenever the cyclones are hitting affecting Tamil Nadu coastal or any state's coastal, like there will be some sort of people coming from Indian government, and they will be assessing that, and that will take a lot of time, and that will it is a continuous loop to dispatch money from Indian government to their respective state governments. It will take time, right? But with the help of this kind of tools like remote sensing, AI, we can easily assess like number of buildings affected. We can estimate that, right? Number of buildings affected, or like number of people that are affected, or what are the areas which are flooded, like especially for crops, right? If we could detect the plantations, if you go and consider the regions of Pollachi, or even regions of Delta, you can see like agriculture happening in the scale. It is not 1 acre, 2 acre. It will be like all the farmlands are connected together. So in that case, like for 1,000 hectares, it will be just paddy, or certain hectares in Kumbakonam or nearby Delta regions, it will be only beetle leaves. In Trichy or south banks of Kaveri, it will be just plantain, right? So whenever you, so all these crops can be mapped, all these crops can be detected through remote sensing images, plus by using any segmentation models or any machine learning models for crop mapping. So now if we have the crop mapping, if we assess the flood extent, so we can easily calculate the flood affected plantain area, how many acres of plantain have been affected, how many acres of paddy have gone in floods. So all those things you can do. So this is what 2 different buckets have taken. It can be anything. It's a perception only. For explanation perspective, I have taken. Let's get into first problem. The first problem is urban water bodies. So urban water bodies can be anything. Like it can be tanks. Tanks means smaller man-made lakes kind of thing. Lakes, and if a particular urban area has any reservoirs or any maybe like in Chennai we have, right, like Pundi, Sembrambakam, all those lake reservoirs we have, right? So to track the water levels, like how much water is there, like what water extent we have, and water quality parameters over time. For example, water quality means like is there any algal blooms are there, or algal blooms, like eutrophication. Because of eutrophication, a lot of algae would grow in that particular place. Eutrophication is nothing but sudden hike in nitrogen kind of minerals in that. So if the minerals are high, it is not usually happening. It's actually because of some waste waters, or garbages, or maybe some chemicals are contaminating that water. Because of that only, the eutrophication happens. Because of eutrophication, more algal blooms will grow. If the algae are if the chlorophyll content is high, it will indicate, or it will actually impact the quality of water and the ecosystem, which means the fishes or other animals, like water animals, would suffocate and they'll tend to die. Right. This is what the pain point or the problem of any water bodies and its pollution is, right? To monitor it, because like we cannot. So there are two ways. One is in situ monitoring, where we deploy people and collect water samples and continuously taking it. That's how, like in newspapers you would have read about, like the Tamrabarni rivers contaminations, or even like Noyal and Amravati in Tirupur and Karur areas, right? Like the contaminations are happening from the dyeing factories, and that causes a lot of turbidity in water, or a lot of foaming, right? You would have seen like the entire area is kind of foamed, or some places it will be too much of weeds in the water, or too much of eutrophication in the water. To monitor everything, these are the quality parameters, and also water levels are also there, right? Like how much, whether it is going beyond the extent of that water collection area, which will lead to flooding, or does it going to the like very usually we call that a zero level, or some levels to monitor, like beyond this, if a particular water body goes down to the particular water limit, water level, it might be a drought, or there is no water existing, right? So for that only we use like a lot of insight to things, but to avoid them, to monitor in a large scale, we can use simply we can use Google Earth Engine to actually calculate or to detect the water bodies and their areas. You can see, I think like this Google Earth Engine is visible to everyone. I'm just checking. Yeah. Yeah, it is actually loading on screen. So I have taken the Coimbatore near area surrounding the Ukadam lakes, Valankulam, and other lakes, just to detect them, and just to calculate the area, how much water collection area is there. So for that, we are using, there is a index called water index, a normalized difference water index. So this is actually calculated with the help of B3 is nothing but a code for B2 is blue, yeah, green and near infrared. And the reason is the green element will be completely reflected with the water, whereas the near infrared will be completely absorbed. So when we take the one second, yeah. So this is the NDWI, which is just a water index that has been calculated. You can see the difference between the usual vegetation or surface with the water. So normal blank areas are like normal surfaces where the vegetation is not there. It is in the yellowish in color. Where vegetations are there, that is dark greenish in color. But in water storage area, like which is lakes, you can see the like a dark or aqua blue. This is actually an aqua blue in color. So this is actually based on the values only, like it will vary between -1 to +1. If it is greater than 0 or 0.5, we can consider that as a water. And for that water, we can map them, or we can segment it out with the help of segmentation models, unit or anything. If you just see like RGB colors, that might not be very clear. But if you use like NDWI or NDCI is nothing but to know about the vegetation, or sorry, not vegetation, chlorophyll content in the thing. If you use NDTI, it is just a turbidity index. So most of the places, most of the stagnant water, we may not like notice the turbid conditions, and it varies with respect to rivers and other places also. For example, here I have something like one second. Yeah, this is like for a particular basin, which is delta region in a country, like I think it's in Southeast Asia. So where we are monitoring suspended sediments. So suspended sediments is nothing but like water is too turbid, and also it has a lot of kind of segregated or clay particles, like mud particle or anything, right? You can see this like milligram per liter, like in certain places it is in darker blue, which means like there is no suspended chemicals, suspended elements. But here you can see the sediments, like in this area the sediments are too high. It is because of it could be because of sudden flood, or it could be because of anything else, like maybe some agricultural activities, or maybe the wastewater or some contaminated waters are coming in that particular place, because it is to actually distinguish the clear water and the sedimented water, right? The same way we can use it for here actually, like a specific, you can see the equation. Yeah, one second. Yeah, you can see the specific expression being used, which means this is like with the help of machine learning or a statistical estimation based on insight to data collection. Because certain elements we cannot collect it or measure it with just calculating the normalized difference between red, green, blue kind of bands. So that's why we would require a machine learning and insight to data collection, where we can collect data for very few sampled areas based on experimental design, and then we can fit the model across the nation, so that we can get the um, um, precise measurements for the entire area of interest. So this is for lower Mekong basin, that is in actually nearby Laos or some other Southeast Asia country. So because I tried it for like Valankulam and other places, but the problem is like we couldn't see much contaminations or any algal bloom kind of things like that clearly seen. That's why we've taken like some other examples. The same way, but for this particular area, we can use it for let's say, yeah, measuring the water extent and other elements like average water capture area or capacity. And then on top of that, we can bring in more analytics, like what could be the flood affected areas, or what could be the maybe like the site selections for certain lakes or anything. So those kind of things can be used, that we can discuss in the further slides also. And you can see these other statistics calculated, like what is the water ratio from area, like how much is it, 0.05, and what is the water collected area, it is 4 square kilometer, and the total area is 71 square kilometer. And there is another use case for farmers to actually so farmers, they can monitor their aquaculture things, like if they have like aquaculture water bodies, they can monitor it, they can measure all those, like turbidity, chlorophyll, all those things, they can monitor it. And yeah, this is for urban water bodies monitoring. And then we have one second. Then we have plastic-free rivers or plastic-free water bodies. So this is actually a pure play drone plus AI-driven thing, where most of the water bodies are like contaminated with floating plastic garbages, to detect them, to find where most of the plastic accumulation is there, so that they can take necessary action to control it. For example, like if you take the rivers or even lakes, people tend to throw or dump plastic waste. To detect them, like of the floating plastics and their number of their quantity, their counts in a certain area, we can use object detection. It can be anything, like any object detection models. But for that, we need to collect data using drones, because for plastic, they are like their maximum size could be some 1 meter or less than that, right? Plastic bottles or any plastic garbages. So for that, we cannot rely on remotes. We cannot rely on satellite imagery, whereas we should go ahead with drone imageries, because drone images are like high resolution. They are like with 2 centimeter resolutions per pixel, or much lesser than that. So in that case, we can clearly see plastics. You can see this plastics, even this blue or like whitish colors are plastics. Like these are like just scattered, but in many places the plastic could be like accumulated, or within a certain area that could be like accumulated, right? So once we detect them, if we by geotagging them, by creating a dashboard kind of view where we can create a heat map in such cases, like we can navigate to high dense plastic accumulations, and that thing could help us to navigate so that we can remove it quickly, and we can find the root causes, which are all the sources that cause the high plastic accumulation. Is it like a certain community or a certain society dumps, or an individuals, or commercial organizations, right? So that is for plastic free rivers or water bodies. Two. And the third one is like monitoring flood and assessing the flood affected areas. So this is actually a typical change detection problem. So change detection is nothing but to detect the change or the difference between one time period to the another time period. Because if you just say flood is nothing but like an unexpected and also a rare condition where the extensive water is coming, right? Or because of the rain or because of other water bodies. Because if we just monitor water bodies, or if we just use one element, which is having NDWI, which is water index, it will just give, okay, water is present here, but we don't know whether that water is permanent water, or a sudden water, or sudden flood, right? So that's why we need specific calculations which can actually detect the change between normal condition and the flood condition, which is more or less like detecting the difference in the distributions, two different distributions. For example, in hypothesis testing, we use a t-test to estimate whether two distributions are statistically different or not. We use like KL divergence, where the same thing, like what is the distinction between two different distributions, right? So this is the statistical way. The same way we can deploy our machine learning algorithms to find the changed areas where the new water comes in, where we could see like this particular segment of area is newly detected as water, which could supposed to be a flood affected region. So this is for hurricane. So for a certain hurricane example in America, in southeast, which is around like Dallas, Texas, and other areas, maybe. Yeah. So in this particular river delta region, right? I'm just showing you the permanent water first. So you can see this like these are all the backwaters, or where the bigger rivers tend to make lagoons or delta areas, right? So I'm just selecting permanent water. So these are the permanent water, and you can see the river also, right? The river also. And we wanted to know like flood affected area and their extension, right? On what extent the flood is being affected, so that two things. One is like we can evaluate the more flood affected areas, and another one is we can also estimate based on other informations like the crop mapping of that particular area, and also the building concentration of that another area. We can try to estimate the losses, right? So I'm just helping you like during the cyclone, during the hurricane, where are all, like we can see the excess water. You can see this particular bluish colors, or the extra flood happen in the hurricane, during the hurricane, and after hurricane, which is like extension of the particular hurricane, which is the post math effects. I'm just removing this. Yeah, it's getting calculated. It's okay. I'm just adding another layer, flat plane. Yeah. Yeah. This pale bluish color, right? This pale bluish color is the place where the flood is affected, right? For example, if you could see this particular area, these are the flood which is kind of scattered, right? But if you could see this particular place, or maybe this area, like it will come, like, because it is actually on computing, like it's computing based on wherever places we load. So yeah, this entire city, right, this is actually like kind of affected a lot because the area extent itself is high for this particular area. But when we see the other areas, that is less. So it will help the municipalities or the governments to prioritize where to go and which one to give more importance, right? So, and for that we might need further informations like where buildings are there, and where what kind of crops are being cultivated. For example, we have crops like teak wood, or maybe some certain areas people would just grow trees for timber woods, right? The cost incurred, or the damage incurred in that particular area would be much more higher or lesser comparative to other plantations. For example, if you take or paddy or plantain or even some other crops, right, that would tend more damage with this much high higher flood than the places where we are growing trees. For example, in Polachi, even if we get more flood or something, like maybe the damage would be lesser because most of them are growing coconut trees, which is which can withstand the flood than the. So based on this information, crop mapping information, where more like plantations or vegetations are there, certain crops are being cultivated, based on that we can evaluate the damage caused by that particular thing, right? But you might ask, like, how would I able to get it, right? There is two things. One is like there are a lot of online data sets available where the entire world crop is being mapped, or for India also we have crop mapping. And for buildings, right, I'll come to the later part, like for buildings, once again, yeah, we have recently Google has open sourced their buildings data set. So they have used UNIT on 0.5 meter resolution images to detect the buildings in a particular area. So here I have taken a snippet on. It's also like around Coimbatore only, and it's nearby Valankulam. So this particular data set will help you to perform too much like many projects. Like we can do population monitoring, where we can estimate more population density, and this would help commercially also for municipality. They can use it for um, like they can use it for like certain things like vaccination planning, or maybe if they are running some campaigns, or if they want to build something like some government institutes or some government initiatives that can be helpful for them to identify. So these are all the potential use cases, and there should be a mentality to adapt it also. People might say that, okay, we have resources, we can just based on the people requirement, but that's the problem. One typical example that I would suggest is the new bus stand in Coimbatore, right? That is being in dispute. People are like, one group is saying Velalur and another group is saying some other places, right? So it is actually the problem of optimal site selection, right? Without knowing like more people or roads where the congestion are there, where the possibility of floods happening, or the proximity to like other potential spots like railway stations, or for example in Bangalore, that is the problem. Like everything is like the airport is far away from all the other places. It's far worse than Chennai, because at least in Chennai everything is interconnected, or at least nearby each other. But Bangalore, it is completely different case. The same case for Coimbatore also. If something new comes in, it should also um, like based on, it should be selected based on certain things like how proximal is it to particular other popularly used places, or what is the flood prone measurement, or what is the risk of a high flood or high water logging, or is it, do we have any other things? So all those things comes under like a site selection. For that we might need other point of interest, like where more buildings are there. And we also have OpenStreetMap where we can get point of interest like parks and other things, right? So all those things will be helpful for us. The same way we can use it for environmental monitoring, where if there are any carbon emissions, right? With the help of this remote sensing bands, we can measure the carbon monoxide and nitrogen emission. There are certain equations, certain models are available. With the help of that, we can monitor it. By overlaying this with buildings, we can estimate like which building or what could be the, because we have this addressing systems also, which means each and every area has been given with a certain plus code. That plus code you can notice in Google Map also. And then by overlaying different kinds of information, like the remote sensed carbon monoxide or any emissions with this kind of buildings data set, we can navigate to the certain places. And also we can estimate the energy requirements, like which place would require more energy. Based on that, they can deploy like substations, or like the location for transformers and other places, other required resources, right? And the same thing for, as we discussed, like flood affected areas, we can simply calculate with the help of flood extent with the overlay of buildings, how many buildings would have affected. Based on that, how many people would have affected, and the required numbers of resources, like disaster relief battalions, right? So the use cases are there. It's up to us to select different things and trying out. So I just wanted to like give a common framework for it. Like for any RS analytics, it will be 3 different parts. It is not just always modeling. It will be all 3 of them are like important, because the scale of data is so large, and also we need to use our engineering mind to optimally use resources, or like perform distributed and parallel computing, right? So based on the problem definition, we can select data sources. The data source can be anything, like it can be Sentinel or Landsat. For that only, like you can visit Planetary Computers. So Planetary Computer has a lot of cataloged data sets. Also, you can use Google Earth Engine also. So both of them are available. For example, I would suggest Microsoft Planetary Computer, because that is more Python centric, and also you can get something called cloud optimized images. So cloud optimized images will reduce the memory required, and also the inbound operations, like memory inbound and IO operations easily, and that can be easily quickly shareable. And it is common catalog, so that anybody can utilize it with the help of this particular catalog called STAC. So you can Google it, like spatio-temporal asset catalogs. Like all the whoever creates new satellite imageries right now, these days people are like following spatio-temporal asset cataloging. So this will help for easier navigation, easier indexing, and discoverable. Because the thing is like if we don't have any catalogs, or if we don't have anything, like we need to go image by image and check that whether our location is present in that or not. That's why we're creating a dictionary kind of things, or an index kind of thing. For each and every asset, we'll be having like what is that area covered, and what is the bounding boxes, which means like that the location information, and what information is being collected, whether it is green or near infrared or anything. So those kind of things can be captured in the STAC stack. And we have planetary computers where you can easily get access to all the data sets. You can use this data catalog where we have Landsat, MODIS, Sentinel-1 is there. Sentinel-1 is radar. So radar is used for like capturing this surface behaviors. It is not for vegetation or anything. It is more or less for like what is the elevation or what is the depth, water depth, all those things we can use it for it, for radar information. And level 2A is there. So these are all for important resources. You can select it for specific things like biomass, forest. The same for demography. We have like census data, and for the entire worldwide, few of them are there like land use, like what is being used for that particular land. Like is it for real estate, or is it for agriculture area, or is it for small urban? The same for our infrastructure as we have. Like here we have this Microsoft footprints. The same thing is like how Google buildings data sets are helping. The same way here you can also use it. And we have other things like solar, water, and weather. So this will help in terms of like mitigation, weather mitigation. Also in terms of like for farmers, it will help. So this data catalog, you can use it. So for problem definition, it's up to you. Like we tech for good, I have already given a lot of problem statements like e-wastage, I think like environmental monitoring, other things are there. Based on that, we can select the data sets and automation of data collection. Like you can follow this particular notebook, a specific notebook. For example, if you select anything like modest bond area, there are like specific notebooks are available. You just need to like request access, or you just need to sign up, and you can collect the data. For that, to process the data, you might ask the question, like for data processing, there is something called X-rays you can use. X-ray is a multidimensional data processor. Like you can use it along with DASC also. So this will help you to handle the satellite imageries for performing like parallel computing or distributed computing. You can use DASC. I think like DASC will help you a lot to reduce the time required for processing, because all of them are like in GBs of size. So you can certainly use DASC, two of them. To automate it, you can use anything like Airflow or any sort of libraries. And for machine learning, I would suggest this particular thing for anything related to remote sensing based thing, which is Torch Geo. The reason is like data handling, right? The data handling and certain data sets are pre-trained models are already available in Torch Geo. There are other libraries also, Radiant Earth, and Sentinel Hub, all of them, they are data providers. But Torch Geo seems to be like a compact one where you can create data sets, data loaders with respect to geospatial use cases, because in geospatial, they're sampling the way that we sample data, that would differ, and different transforms, and also pre-trained models. So here the pre-trained models are not ImageNet pre-trained, they are pre-trained on larger remote sensing data sets, so that transferability, right? Whenever you are doing transfer learning, compared to ImageNet to your domain, when you do in-domain transfer learnings, in-domain fine-tuning, it will be much more easier and also very relevant, and the model will be able to easily converse. You can read about it. Like even I have written like a LinkedIn post on it. Like recently, there is a library called SSL for EU. So this is a data set, and this data set covers like entire world, mostly almost the world level pre-trained models are available. Like it covers multiple locations, multiple seasons, and multiple modalities, which means different satellite it covers. And based on that, people have used self-supervised learning for pre-training their model, so that this representation, so like whatever pre-training model that we have here, ResNet 50 and VIT, vision transformers are available, that you can use it for whatever model you use. For example, if you are using UNet, you can use ResNet 50 as your backend of the encoder, or if you are using segformer or a mask former kind of transformer models, you can use VIT, right? That is for segmentation or any other task related to spatial things, because like mostly spatial models are like kind of segmentation plus regression models, segmentation models. So you can use it for either instant segmentation or semantic or panoptic, or if we are just using it for let's say scene classification, which means just to classify whether it is urban area or whether it is water body or not, we can also use it for as a backend of your classification models, right? So and the change reduction, for change reduction also, any unit or any auto encoders you are taking it, the backend the encoder part can be replaced with this particular pre-trained models, right? So coming back to the problem statements, like the problems can be any problems. Like if you take any problems, broadly, this will come under three things. One is scene classification, whether to classify certain patches, image patches, whether it is comes under agriculture land or suburban land or anything, or change reduction, as I discussed before, like difference between two different scenarios, T1 and T2. What is the change, where the change has happened, whether the change is because of deforestation, or is it because of a high flood, or is it because of urban development, that you can define it with further metadata. And segmentation like for the like land uses, water bodies monitoring, and building detection. For building detection also, segmentation only the solution for that. Or for land, crop mapping, right? For the extent of area, what is being planted, like whether it is coconut or a mango or plantain or paddy, all those things you can use semantic segmentation. Or even for agriculture land parcels, right? For that monitoring, to detect the boundaries of agriculture farms, or to detect the boundaries of your streets, or maybe whatever assets you have given, you can use segmentation. But the core solution is not being stopped here itself. We need to perform analytics over area and time, so that only we can get metrics like how much is being caused or how much is being damaged, and then we can use optimization on top of that, so that we can deploy optimal we can do optimal site selection or optimal resources management. All those things we can do. So this is the three different steps. For each of them, I have given like I've just discussed one or two. For this, you can simply use Tableau or any Python-based analytics tools. But for this, you can use StarGeo, or if you can convert things into TensorFlow records, you can simply use Keras or PyTorch. Directly, you can use it. But TarGeo is specifically made for remote sensing activities. And for here, you should use more and more X-ray, DASK, along with some parallel or like some workflow management tools like Airflow or maybe Prefect or anything. Mostly you can use Airflow. And DASK itself will be able to manage that distributed computation with the help of the lazy compute, all those concepts, right? Yeah. So this is what like I wanted to cover from the fundamentals of remote sensing to different problems available and how we can approach it, and the tools required for it, and the data sets availability, right? And if you want to solve a certain problem, which is very specific problem to your locality, you might need to spend more time on this data collection or data labeling, especially because we are spending a lot of time in data labeling for our use case. The same way you might require it for data labeling. But even if you have very lesser amount of data, you might do it semi-supervised or like self-supervised learning. That we have contrastive learning models are available as a packages that we can use it for your use case. But one thing is like based on problem statements, we might spend more time in data labeling part for better accuracy, because the landscapes are changing over time. For example, it's more or less like a language only, right? English is being able to solve, but we have very limited number of models for low resources languages, right? Like Tamil or other regional languages. It's the same way. The landscape and also the structure and the lifestyle of a certain area completely differ from others. For example, if you want to monitor water bodies or aquaculture or agriculture areas in West or in the European countries, all of them are properly delineated. All of them are like properly structured in square or some other shapes. But for here, we do very random cropping. Most of the what we call this the seasonal or non-seasonal crops, most of them are like kind of scattered. They are not cultivated in a scale. Very rare, like a paddy or like a plantain or coconut are being cultivated at a scale. Other things like oil seeds or anything are very less in nature. So that's why we might need like very specific data labeling. The same for water bodies also. Based on the use case, the data labeling might differ. Data labeling is nothing but we annotate it. Also, we collect some insight to data from the ground, right, for better like feedback to the model and also for better features for our model, right? Yeah. If there are any questions, we can discuss it around.